the odds ratio. We're going to look at another way of talking about this idea of a good decision based on dependence and independence, and once again, our key concept will be information. So we're going to define the joint information difference for events A and B as this delta sub I, A comma B, is this sum, I10 plus I01 minus I11 minus I00. If A and B are independent, then according to our theorem, the joint information difference is 0. If B is totally dependent on A, then you can show the joint information difference is actually infinity. And we'll look at this definition again in a later lecture. But let's look at an example. So Jane chooses from 3 cards numbered 0, 1, 2, and then John chooses a card. So capital X will be Jane and capital Y will be John. And our sample space looks like this. The probability of each event in the sample space is 1/6 because each of these events is equally likely. So our events will be A, Jane gets a 0, and B, John gets a 1. They're not independent. B, what happens in B depends on whether or not A or A prime occurs. If Jane chooses 1, John cannot choose 1. And dependence then relies on A, B, A prime, and B prime, and here are A, B, A prime, and B prime written in terms of the actual card pairs that would be in there. So we have 4 events. The probability of A intersect B, the probability of A and B simultaneously, is that single card pair, and that's a 1/6. And therefore the self-information from A and B simultaneously is the log base 2 of 6. It would actually be the negative log base 2 of 1/6, the probability. Likewise, the probability of A intersect B prime. A intersect B prime is one pair of Jane-John selections, and there's the self-information. Similarly with A prime intersect B. But now, let's look at what happens when we do the probability of A prime intersect B prime. So I've written A prime and B prime staggered so you can see that they have 3 card pairs in common. And therefore we have a probability of this is 3/6 or 1/2, and therefore the information here is the log base 2 of 2, which is 1. So we compute our joint information difference, and you can see clearly that it's not going to be equal to 0. In fact, it's going to be the log base 2 of 6 minus 1, which is about 1.58 bits. So what does this mean? Well, before we say what it means, let's notice that we do something very often when we talk about probability. We tend to answer questions or do theory with information. But we tend to apply theory via probability. So we're going to let P sub ij be the associated probabilities to I sub ij, and therefore when we calculate the joint information difference, we get negative log base 2 of P10 and minus log base 2 of P01, and so on and so forth. Using properties of logarithms, we can combine these sums into products, and then differences become ratios. And for reasons we'll soon explore more fully, we're going to define this to be the odds ratio, this P11 P00 over P01 P10. But before we do that, let's look at contingency tables, in which we have a large number n of observations of some experiment with variables x and y. And so we'll create a two-way contingency table of counts. So x not in A and x and y not in B will have count 0, 0. And so therefore the totality of x not being in A, or x being in A prime, is count 0, 0 plus count 0, 1. And likewise, in a couple more slides, we'll look at the count 0, 1, 0 plus count 1, 1 for x being in A. So if n is very large, then the conditional probability that y is in B given that x is in A, that's the probability of the simultaneous y in B, x in A, over the probability that x is in A, and that's approximately the count 1, 1 over count 1, 0 plus count 1, 1. So we're going to call this frequency tables. We're going to divide the numerator and denominator by n, and then we'll see that the probability that y is in B given that x is in A is the count of 1, 1 divided by n, and 1, 0 divided by n, 1, 1 divided by n, and that's going to give us our probabilities. And so now our two-way table is what's going to be called a frequency table. So x naught in A is counts divided by n, and we're going to replace all that by probabilities. And notice that it's actually probabilities only in the limit as n goes to infinity. So that means we also have the conditional probabilities. Probability of y in B prime given that x is in A is approximately the ratio of these counts, which is the probability of 1, 0, the probability of 1, 0 plus the probability of 1, 1. And if we take the ratio p sub 1, 1 over p sub 1, 0, then that would be the same as p sub 1, 1 over the sum of the two, p1, 0 plus p1, 1, p1, 0 over p1, 0 plus p1, 1. And so that's actually the ratio of these conditional probabilities. And this is what we would say is the odds for y given that x is in A. So if A is the entire sample space, then the probability that y is in B given that x is in A is just the probability that y is in B, which is just the probability of B. And in this case, the ratio p11 to p10, when A was the entire sample space, would just be the probability of B over the probability of B prime, and that's the odds of B. So if we define the odds of B given A to be this ratio of the probability of y in B given that x is in A over the probability that y is in B prime given that x is in A, then P11 over P10 is the odds of B given A. Similarly, we can now go back and use that other row, and we'll get similar results. We'll have two conditional probabilities, probability that y is in B given that x is in A prime, probability that y is in B prime given that x is in A prime. We can write these as in terms of the little p probabilities, and therefore the odds of B given A prime is the probability that y is in B given x is in A prime, probability that y is in B prime given x is in A prime, and that's P01 over P00. And remember, we defined the odds ratio to be P11 P00 over the mixed P01 P10. It follows that we could rearrange so we have P11 over P01 and P10 over P00. And this would be the odds of B given A over the odds of B given A prime. And because the odds ratio is the ratio of two odds, which are themselves interpreted as ratios, the odds ratio is likewise interpreted as a ratio. And so the odds ratio answers the question, how many times more likely to get B given A than to get B given A prime? Now let's go back to our frequency tables. If we have a very large number n of observations of some experiment with variables x and y, then we can replace the probabilities by counts if the n is sufficiently large. And so we can go back to our concept of the counts with the two-way table. And in this sense, the odds ratio would be the ratio of count 1, 1 times count 0, 0 over count 0, 1 times count 1, 0. So let's look at an example. So we're going to look at mountaineers descending from Mount Everest between 1978 and 1999. So we're going to have event A is going to be mountaineers that used supplemental oxygen, and B is going to be mountaineers who survived the descent. And here's our actual data. So there were 8 who did not use supplemental oxygen who died. And there were 88 who did use supplemental oxygen that died. But notice that there were only 32 that used supplemental oxygen and survived, and 1,045 who used supplemental oxygen and survived. So if we look at this in terms of probabilities, we're going to divide by the total number of mountaineers. Then we get these ratios. And so we get the P00, P01, P10, P11. And the odds ratio is therefore going to be about 2.9588. In other words, about 3 times more likely to survive with supplemental oxygen than without. So let's interpret this. The odds for survival given supplemental oxygen, that's the odds of B given A, is P11 over P10, which is 11.87. So you have an odds of about 12. In other words, you're about 12 times more likely to survive with oxygen. And the odds for survival without oxygen, that's the odds of B given A prime, they're only about 4 times more likely to survive than die when you have no oxygen. And the odds ratio is odds is a ratio of odds, in which case we have the 11 over 4, which is about 3. An odds ratio answers the question, how many times more likely for B to occur given A than for B to occur given A prime? And it follows that the log odds ratio measures how much more information we obtain from an occurrence of B given A than we obtain from an occurrence of B given A prime. So it's the joint information difference, which is in terms of bits or information or nats. So for a classifier problem, A tends to be the event of a given observation being an actual positive. B is the event of a given observation being predicted to be positive. And the contingency table then becomes the confusion matrix. So we have event A, it really is negative or positive, and B, it's predicted negative or predicted positive. And we can think of these in terms of counts. And because each of these basic metrics can be restated in terms of counts, that means they can also be restated in terms of these small probabilities, these index probabilities. And therefore, they also can be restated in terms of the informations. So conditional odds are given by P11 over P01, which is true positive over false negative. And the odds of B given A prime is false positive over true negative. And therefore, the odds ratio is the true positives times the true negatives over the false negatives times the false positives. The joint information difference states this confusion matrix idea in terms of information in bits as shown here, or in nats if we use the natural logarithm. And so now we're ready to move on to logistic regression. One quick note, however, we're only working with binary classifiers in the course, but we can actually extend what we're doing here to any number of classes, as you can see from this table. So the complexity is only in keeping track of more items, not in the concepts